All right, our last problem in this section on empirical and molecular formulas is the most involved problem. This is going to take me a little bit of time to get through, but that's largely because the information that they're giving us has so many walks that we need to do in order to get to useful information that can allow us to determine a molecular formula. So this is what we call a combustion analysis problem. And I just want to go through just a little background as to how this kind of stuff works before we actually use the data. So this is just a figure from your textbook that shows combustion analysis. Oh, let me show you real quick one thing first. Remember, and this is an equation I want everybody to know, combustion is really the combination with oxygen. So anytime we have a fuel and we combine it with oxygen, that's going to give us carbon dioxide, water, and energy. So an equation that you should commit to memory, that you should always be able to remember, that that's what combustion is. And the key here is most things that are combustible or fuels have carbon, hydrogen, and oxygen as part of them. So the concept is that when you combine this with oxygen, the carbon from your fuel gets converted to carbon dioxide, the hydrogen gets from your fuel gets converted to water, and then whatever is left, that oxygen just is going to be what we call the difference. Hopefully this will make sense in a second here. So, but the concept is your fuel basically gets converted to carbon dioxide and water. So what we have here when we do this combustion is we have this combustion chamber. So a stream of oxygen comes in to a sample combustion chamber. So you're going to put your sample in here and you're literally going to light it on fire. And you're going to produce your carbon dioxide and your water. You have a drum here that absorbs water. You have a drum here that absorbs carbon dioxide. And the concept is we're going to weigh these absorbers before we do our reaction and after we do our reaction. And so we'll be able to take the difference in those masses and figure out just how much water came from combusting our substance and just how much carbon dioxide came from combusting our substance. And then again, other substances that are not absorbed will exit out this way. So I wanted to make sure that people understood kind of conceptually what happens in a combustion reaction and with this acquisition of data, because I think it'll make understanding what to do with the data a little bit easier to understand. So in this problem, they tell us that we have a 1 gram sample of vitamin C, and just like our previous problem, they give us the molar mass of that substance. So we're going to be building on the problem that we just did, problem 3.10. We're going to need to take some data, and then we're going to need to figure out an empirical formula, figure out the mass of that empirical formula, compare it to the mass of the molecule that they tell us we have, and see what we need to do to scale. Okay, so we're going to set up this walk first. And again, this is going to be a fairly lengthy walk here. So, and then we'll relate it to the problems that we've already done. So we've got a 1 gram sample of vitamin C, we put it in our combustion chamber and we burn it. And here's the following data that we obtained. We've got the mass of the carbon dioxide absorber before and after combustion and before. So hopefully it makes sense, and why I showed you that picture is the difference is going to be equal to the CO2 from our combustion. Okay? And then this difference is going to be, the difference is going to give us the water from our combustion reaction. So remember, we're going to make carbon dioxide and we're going to make water. And we're going to be able to relate those back to the amounts of carbon and hydrogen that were in our samples. Again, this problem, I know it's going to kind of make your brain hurt a little bit. You might have to watch this video a couple of times to kind of make sure that you understand what's going on here. But the idea is if we want to figure out the amount of carbon that's in our sample, we need to get that from our carbon dioxide data. Okay, so the difference between these two numbers, okay, is going to be equal to 1.50 grams of carbon dioxide. Okay, so follow me along with this one and see if this makes sense. Okay, we're going to use this mass ratio here. So we know that the molar mass of carbon dioxide is 44.01 grams of carbon dioxide. That's the whole. We want to figure out what the mass of the part is. How much carbon do we have here? Because the combustion reaction added oxygen to the carbon in our sample and converted it to carbon dioxide. So we need to really figure out how much carbon do we have. We get that from the carbon dioxide data, but we need to back out the amount of carbon that's there. So 12.01 grams of carbon. And this is kind of a unit conversion we really haven't seen before. Okay, so it might be a little bit confusing to kind of look at it there. But we're going to use this. This is kind of our idea of relating part to whole. So again, kind of a unique unit conversion, but the mass of carbon, so this is our part over our whole here. Okay, so we're going to take, if we have 1.5 grams of carbon dioxide, we're going to figure out what part of that is just carbon. So that's 0.409 grams of carbon in our starting compound. And I know this problem is always confusing to students, so to make sure you understand, there was 0.409 grams of carbon in our starting compound. Right? We had a gram of starting compound. A little less than half of it was pure carbon. When we combusted it, oxygen was added to it such that now that was 1.5 grams. But we needed to figure out there was a fraction of that, part of our whole, that was just pure carbon. So we used this carbon dioxide data to get what the starting carbon was in our sample. What we're going to do is we're going to do the same type of analysis to figure out the hydrogen in our sample. And again, we're going to use our water data to do that. Difference between these two numbers is going to give us the amount of water produced from our combustion reaction, and that's 0.41 grams of water. We're going to do the same thing here. If we had 18 grams of water, again, that's 1 mole of water, we'd have 2.016 grams of hydrogen, really 2 moles of hydrogen. So maybe that's a good way to think about this too. Maybe it would make sense to everybody to think about the fact that there would be 1 mole of carbon, right, in every 1 mole of carbon dioxide. So again, we can get the molar masses of these and put those in there. Same thing for here. Okay, mathematically, this works out to 0.046 grams of hydrogen in our starting compound. So we have to figure out what oxygen then was in our sample. And how we get that is from this law of mass conservation. Now we talked about this in chapter 2, but we just talked about it conceptually, and I said, don't worry, in chapter 3, we'll get to actually use the law of mass conservation. Remember, this tells us if we had carbon and hydrogen and oxygen in our fuel, and we had 1 gram of our fuel, if we just figured out how much was carbon and how much was hydrogen, does it make sense to everybody that the difference between these and 1 gram is going to be the oxygen in our sample? So see if this makes sense. 1.000 grams of sample minus our grams of carbon and minus our grams of hydrogen will equal grams of oxygen. So 1 minus the contribution from carbon and minus the contribution of hydrogen will equal our grams of oxygen, and this equals 0.545 grams of oxygen. Wow, so now we have the fact that there was 0.409 grams of carbon in our sample, 0.046 grams of hydrogen in our sample, and 0.545 grams of oxygen in our sample. Again, just do a little test, make sure that those add up to 1 gram, and if you really wanted, you could actually go and do kind of a mass percent. Okay, but again, that's not going to get us back directly to what we have here. But what I will tell you is that gets us back to what we had for sample problem. Oops, that's our ionic compound, excuse me. It gets us back to kind of where we were on sample problem 310, where we had mass of our sample. So I'm going to grab another piece of paper here, but what we're going to do for this compound is we're going to walk from masses of the substance to moles using molar masses of the elements, get our empirical formula, molecular formula. Again, compare the empirical formula's molecular weight to the molecular weight of our substance, and then we'll see if we have to do any scaling. So I'm going to write out that roadmap to make sure it makes sense to everybody. Okay, so again, here's the problem that we're working on. And we're basically going to take the mass that we have in grams of each of our substance, and we're going to use the molar mass of each of these elements, and we're going to convert it to moles. And then from moles, we can go to our empirical formula. And again, empirical formulas being the simplest whole number ratio. And then we need to go to a more molecular formula. In order to get from an empirical formula to a molecular formula, we need to compare the molecular weight or the molar mass of our empirical formula to the molar mass of our substance. And again, we'll have to see if these are the same or if they need to be scaled. Okay, and so I want to make sure that everybody sees that once we used our combustion data to get to our mass data, we're exactly like problem 3.10. So I'm going to go through that a little bit more quickly because we've already done sample problem 3.10. Okay, so again, our mass data that we have here is we've got 0.409 grams of carbon, 0.046 grams of hydrogen, and 0.545 grams of oxygen. Okay, taking each of these and converting them to moles, I'm going to use the molar mass of those substances. Hydrogen, again, 1.008 grams of hydrogen. 1 mole of hydrogen, 0.046 moles of hydrogen. We've got 1 mole of oxygen, 16.00 grams of oxygen. I want to make sure to point out here just something that sometimes can be confusing to students. We used 2.016. We used 2 of the atomic mass for hydrogen here because we were talking about 2 moles of hydrogen atoms here. Here, it's just 1, so that's why that number is different. I want to make sure that everybody saw that. That's a common question that students have. So this is 0.0341 moles of oxygen. Again, to get to an empirical formula, we're going to divide by the smallest number, which is 0.0341. Okay, that's going to get us to our empirical formula. So we're going to get C3H4O3. So that is our empirical formula. Now remember, to go from an empirical formula to a molecular formula, we have to calculate the molar mass of our empirical formula, and then we compare that. So the molar mass of our empirical formula is 88.06 grams per mole. So again, this is the empirical formula. Our substance, kind of coming back up to our page here, remember they told us that vitamin C has a molar mass of 176.12. So our substance molecular weight is 176.12 grams per mole. Hopefully everybody can see that this is a 2-fold increase. So that means we need to scale our empirical formula by 2-fold to get our molecular formula. So we've got C6H8O6 as molecular formula for vitamin C. Again, quick, easy check. Calculate the molar mass for this. And again, the molar mass is 176.12 based on this. So a great internal check. Some of the problems that we're going to do are going to have these kind of internal checks where you can kind of have a way to double check your answer. And this is a perfect example of that.